Good morning, students. So today we will continue discussion on the interfacing of input-output with the 8086 microprocessors. So as we discussed in the last class, right? So uh, basically we have two kind of mapping of input-output devices. One is memory mapped I/O, another is I/O mapped I/O. Okay. So in the last class, I think I stopped up to the important requirements. How do we demultiplex the address information from the multiplexed address data bus of the processor? And we have also seen that there is an IC that is required called an octal latch, right? So you need to have a latch, and we also require a decoder. So we have discussed that another requirement of the interfacing is that decoding. So once you have an input device or an output device, to be interfaced with the microprocessor. So every such device need to be given an address, unique address, port address. Okay, so in order to derive that selection logic, right, the port selection, so we have to have some kind of address decoder. So that is what we have discussed in the last class. So let us continue discussion with that, and especially, yeah, we will see. We have seen about how the switch is going to be interfaced. So in our first discussion, we are going to discuss about how exactly the uh, key switches are going to be interfaced. Okay, so key switches are going to be interfaced. So this is our main concern now. Say, so as I already told you, so we can assume that yes, the requirement here is that requirement is that it requires a tri-state buffer, tri-state buffer. Okay, a switch is a device which has got two terminals. So it may be either a push button like this, or it may be a single pole, single throw switch like this. So when you throw the switch, the contact is established. When it is in the normal position, so the circuit is broken. Okay. So either way. So how do I determine the status of this particular thing? How do I determine whether the switch is closed or not through an input port? That is my requirement now. Right. As we have discussed, so this can be interfaced with a tri-stating buffer like this. So let us assume that it is a push button switch. The same thing is applicable to other kind of switches also. So the requirement here is that we need to have a tri-state buffer, right? Non-inverting tri-state buffer. So this should be taken to the processor. This should be taken. So as I already told you several number of times, the tri-stating buffer, right? The output follows the input. Whatever that output is available here, it's going to go. But the tri-stating buffer will also have an enable signal. So this is an enable signal. Okay. Um, so this is called as an enable signal, output enable, right? Output enable signal. So that means since you are seeing a bubble here, so when this particular signal is equal to 0, right? So if this is equal to 0, implies that the output is enabled. Output is enabled. That is, output follows inputs. Whereas if it is 1, the output is disabled. More aptly, we can say the output is at tri-state. Otherwise, we call it as at high impedance state. So, being electronic students, should be able to understand this high impedance state. High impedance state. So, that is the output line is logically disconnected from this particular circuitry, right? So, since the data bus of any microprocessor based system is a shared one, common, and meaning that So at any given instant of time, the microprocessor will be able to communicate with only one selected device. It may be an input device, it may be an output device, or it may be one of the memory device as well. So more than one device drives or participates in data bus, the system will not function, right? Because there will be a collision of the data that is taking place. So we need to permit only one device take part in the communication at a given instant of time. So that is why we can see that these kind of tri-state buffers are used for connecting with the devices. Hope you understand this. Now that there are two questions. So how do I map the on and off status, as I already discussed in the class, in the first class. So how do I do that particular thing? So when the switch is closed, I should get a 0. When the switch is in the open state like this, when there is no connection, I should get a logic 1. How do I do that? Just this arrangement will not do now, because the other end of the wire is nowhere connected. Nowhere connected. So as we have discussed in the last class, I'll just recall, right? So this is one way of doing it. So this can be grounded. So this is a ground symbol. This is a symbol of ground, right? So ground in the sense it is logic 0. It is logic 0. So this is called as a ground. So for my design, so this is logic 0. When the switch is closed, what would happen is that a logic 0 will be going as an input to here. And if this tri-stating buffer is enabled by an external signal, how we are going, how to trigger this particular signal, we will see. So what will happen is that the 0 will be transferred to here. The same 0 will be available here. Buffered. Basically, the output is buffered from the input. Okay. So this 0 will be taken to the microprocessor when we connect it to the data bus, as we are going to see here. Right. So now that one point that we are able to do, when the switch is closed, I am sure that say switch is closed implies logic 0 is being given to the processor. That is when I do in instruction, in port address. So I can understand that okay, logic 0 indicates that the switch is closed by by the user. So either he has depressed that particular thing, or the switch is put into the closed state. Okay. But what happens when the switch is in the open state? Open. Okay. So when the switch is in the open state, right? So normally we call it a normally open circuit. Normally open circuit. So of course 0 is not going. So opposite of 0, the complement of 0 is 1. Whether 1 is going here is a big question. So now when the switch is not closed, so this particular point, the input, I can say this is not connected. NC. This particular terminal is not connected. So the input is indeterminate. Don't care. So I don't know whether it is 0 or 1, right? So in order to make sure that when the switch is not closed, right, when the switch is not closed, logic 1 is applied to the input. So how do I do that? So very simple. So I can connect a pull-up resistor with this particular thing. So we can connect with a pull-up resistor like this. So normally this will be around some 4.7k kilo ohms, and this terminal can be connected to the power supply VCC. Okay. Now hope you understand, when the switch is in the normal, not connected, open state, when the two terminals are not connected, naturally the 0 will not come. When the 0 is not coming, what would happen? The same potential, the VCC will be appearing here. VCC is already equal to 5 voltage. So almost the same 5 voltage will be available at here as an input. So which indicates that it is logic 1. So when the switch is in open state, logic 1 will be connected to here. And when the switch is closed, then what would happen is that this 0 will be connected to here. You might ask, so already VCC is coming, sir, what will happen? So when the VCC is connected, what happens if the switch is closed? The current will be the current will be flowing like this, right? The current I from the power supply would go and then drain at here. So essentially what will happen is that this particular potential will become zero voltage, right? So when it is a 0, it is a logic 0. That's the basic idea. So when the switch is depressed or closed, logic 0 is applied as an input to the buffer, and when the switch is in the open state, the logic 1 is applied here. So that's how we are now doing it. So this kind of inference is now made. Now our challenge is to take this appropriately to the microprocessor data bus. And then this device should be addressed as well. This device should be addressed as well. So how do I take this particular thing? So I can simply connect it to the microprocessor, right? Any of the data lines. So for example, let me connect it to let me connect it to AD0. AD0. Because the 8086 processor does not have a separate data bus. What it has is only a multiplexed address data bus, right? So what we are discussing in this context is that I am trying to get the status of one switch. So that particular one switch need to be inferred via any one of the 16 data lines. Any one of the 16 data lines. The choice is worse. So without loss of generality, I can connect this particular thing to the bit 0 LSB. If I want to take the status of another switch, maybe I will connect it to AD1 with a similar arrangement. And and uh, 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 and if I want to take say 4 switches, then I can connect them to the AD0, AD1, AD2, and AD3 and all, and so on. I can do that. That's the basic idea. So hope you understand this particular thing. So now I can straight away take this particular thing to um, to this AD0. Okay, this AD0 it can be connected. Uh, AD0 it can be connected. So now the question is like at which address? What is the device address? What is the port address? At which address this is going to be read from? Okay. So we will come back to this particular slide. So before which I think I have already told you about decoder logic in the last class. But anyway, let us recap that particular thing. Yeah. So we need to have a decoder. Basically, what we are going to decode is the address decoding, so that the tri-state buffer gets selected only when a particular address pattern is coming here. Only when a particular address pattern is coming. So it is very common in microprocessors that there is an MSI medium scale integration IC 74138, which is very popularly used in all the microprocessor systems. So this is basically a 3 to 8 line decoder, right? So the symbol could be drawn like this. Okay. So this will have three selection lines. You have three selection lines. So S0, S1, and S2. So because it's a 3 input and 8 output lines, so it will have 8 output lines, Y0, Y1, and so on. So maximum 8 lines will be available here. Y7 will be available here. Then you will be having some enable signals for this particular thing, G1 A bar, G1 B bar, and then there is a signal called G2. So these three signals are called as enable signals for this particular um, you know IC. So these are all the enabled signals. Two of them are active low because you are seeing a bar here, and one of them is active high because we don't see a bar here. So that means only when this input is applied 0, this input is also applied 0, and if this input is applied 1, this will act as a 3 to 8 line decoder. Okay, otherwise what will happen is that all the outputs will remain if the device is not selected. If the device is not selected, right, irrespective of the selection line, then which implies all the outputs will be at high state. When the device is selected means G1A bar is equal to 0, G1B bar is equal to 0, and G2 is equal to 1. So in that particular case, so only one of the selected output will be at low because it's active low. Okay, we are seeing active low. So there are 8 outputs. So suppose that I want to make this particular thing low, then my input pattern should be 1 here, that is 0, 0, 1. Suppose that I want to make Y7 as 0, that is I want to select a device connected with the Y7, my input pattern should be all ones. That's it. So, so 2 power 3 is equal to 8. So with the 3 selection lines, I am able to select one out of the 8 outputs, make it active, that is make it active low, provided subject to the condition this 3 to 8 line decoder is enabled by applying a logic 0, applying a logic 0 here, and applying logic 1. If any one of the condition is not met with, that means the device is not selected and all the outputs will go high. That is, none of the devices connected to here will be connected, will be enabled. That is the basic idea. Now coming back to this, suppose that I want to take it from here, the switch status, we are discussing with a very simple illustration. I want to take one switch status. So one tri-state buffer is required. So I want to take it to here. I want to take it to here. So what do I do? That means that I need to connect this particular thing. So I need to connect with this particular thing. So this should be connected from, the connected from the decoder logic, address decoder logic. I need to connect this from the address decoder logic. So now the choice is that in this particular diagram, either I can take it from Y0 or Y2 or Y3 and so on. So the choice is yours. The choice is yours. Okay. Now let us assume that I want to have the following. I want to have the following. So let me partition this. So let me choose my address as the following. The device address, input port address. So I have to first of all define what is the input address at which the tri-state buffer connected to the switch is addressed by the processor. So let us take the following. So because your address ranges from 000 to FFFF 0002 to FFF. So this is in the IO mapped um, IO mapped IO IO mapped IO. Okay, so so you have choice, wide range of subs. Out of 64 kilo space, IO space, you can arbitrarily choose any one of them. You can arbitrarily choose any one of them. Okay. So as an example, let me choose arbitrarily choose such that the device should be selected at the address say 0 um, y0. So let me give it as 00 f6. Okay, f6. Right. So in a program, when I do in al comma 00 f6h, right, in my assembly language program, I expect that the accumulator 0th bit will have the switch status, and your design should be such that this tri-stating buffer, this tri-stating buffer is enabled. This tri-stating buffer is enabled at the address 0, 0 f6. So this is only an example. So you people can try with something else also. That's the idea. Okay. So let us go with this. How we are going to do this. So in order to do this, so what we need to do is the following. Yeah. So you write this particular address like this, expand it. So this becomes 1, 1, 1, 1, and 6 is going to be 0, 1, 1, 0. So this is A0, this is A1, this is A2, this is A3, this is A4, A5, A6, and A7. Okay. And the remaining zeros here will refer to up to A50. For the sake of simplicity, I'll just ignore these things. Okay, we'll assume that it is always 0. We will consider only the lower order address line because this is very important, right? So if you look at here, we have many choices. You have many choices, right? So So, so what I can do is the following thing. I can connect this to S naught, this to S1, this to S2, right? So I can connect the address 0 line of the microprocessor to the selection line 0, 1 to selection line 1, and address A2 to the selection line 2 of the 3 to 8 line decoder, right? So So what will happen? Now 1 1 0. So whenever this line of program is executed by the processor would have placed address 00F6, 00F6. So when the 00F6 pattern comes, so the A2, A1, A0 will be 110. Accordingly, S2, S1, S0 is also 110. So what is 110? 110 is 6. So that means the Y6 will become low. Every output will be at highest rate. So Y6 will be, when it is selected, it will be pulled to low level during that particular moment, right? So this is what exactly we wanted. So coming back to here, so from here in this particular example, the more appropriate thing is that you connect with Y6 of the 74138. It's as simple as that. But the design is still not complete, right? So what will happen to this G1A bar, G1B bar and G2? That remains unanswered. So as I said, the decoder will be enabled only when this is 0, this is 0 and this is 1. If any one of the condition is violated, means that if this is 0 but this is 1 and this is 1, no, all the outputs will remain at high. If this is 0 and this is also 0 but this is not 1 but 0, no, the outputs are not selected. So all the three conditions should be appropriately connected. By looking at this particular pattern, so I have 1 0 coming here. So you can connect this to this particular thing, G1 A bar, G1 A bar, right? The same thing you can connect with G1 B bar also. G1 B bar also. That means that the both of them can be connected together and this be connected to A3, right? So this is going to be connected with A0, A1, A2 and A3 of the processor can be connected to this G1A bar and G1B bar, so that when the processor address is 00F6, because A3 is equal to 0, so this condition is met with. Now one more condition. So G2 should become 1. The G2 should become 1. What should I do? So either you can connect with this particular thing, A4 or A5 or A6 and kind of things, right? So let me suggest it this way. So we will connect with an AND gate. AND gate. You connect all of these things to this particular AND gate. So that is A4, A5, A6, A7. So A4, A5, A6, A7. So four inputs can be connected. So the output will become 1 only when all the inputs are 1. If any one of the input is 0, output will be 0. The device will not be selected. So that way I can do it. So this can be connected to the G2, right? This can be connected to the G2. And one more very important point is that this address, when the processor is issuing address, right? So this does not discriminate in the address lines whether it is meant for the memory device or an input-output device, right? So for us, the designer, the switch is read through an input port. It is not a memory location. So the key signal that we can use is memory or IO/mode. So we have seen that there is a signal coming from the microprocessor. So this will be a look at the diagram, the timing diagram. I'll just recap. Um, yeah, so you can see here for the memory writing. This is about the memory, right? Memory, yeah, memory bar, IO/bar, right? So there, here you can see this is going to low level, indicating that it's an IO cycle. It's an output cycle. Yeah, we are discussing about input. They are also the same thing. They are also the same thing. That means the microprocessor will pull down this M/IO bar signal to tell the external devices that this cycle is meant for IO devices. So when in AL comma 00F6 is done, what would happen is that this will trigger that particular low. So we have to use that one also. If that is not used, so the device will be taking part in the bus when some memory content is taken, when the processor is either reading from or writing into. So this will be selected. So that should be avoided. So we have to use this particular thing also. So the apt solution here is that you can take this. So this is an AND gate. So this is an AND gate. So what you do is that you can connect your M/IO bar like this. This inverter is required here because we want to have a logic 1 here. When an IO operation is coming, this will become 0, this will become 1. So this ensures that only for IO bus cycles, right, the G2, G2 is the input of the 3 to 8 line decoder will be enabled in concurrence with the other set of address lines, right? So that's the basic idea. So this is a very, very important thing. If this is not done, as I said, this is not a complete mapping. This is not, this does not discriminate between the input and the output is considered. Understand? This does not discriminate between input and output. Okay. So that's the point that you should understand. Okay. This is a very, very important thing. Okay. Now, so I will. So we have now seen that yes, um, how to connect the switch, one switch, how to connect that with the decoder logic, and how do you derive that particular address from this particular example. Hope you might have seen this. The same thing can be extended. The same idea can be extended for many number of switches as well. Many number of switches as well. So so already because we have spent about 20 minutes on this particular thing, I leave it for you to extend this particular logic with application of the tri-stating buffer, commercially available tri-stating buffer such as 74244 that we have discussed in the last class. Okay, so the circuit diagram will come like this. I'll show you. Yeah, the circuit diagram will come like this. When you complete the circuit, it will be like this. So regarding this LED, the output port we will discuss later. Now we will discuss only about the switch array in this particular class. Have a look at this particular diagram. So this 8086 microprocessor, the address data bus, multiplexed address data bus AD0 to AD15 is connected to 74373, which is basically an octal latch. An octal latch. So 8 number of latches are available in this particular thing. So with this particular thing, what do they do is that A to A0 to A things are separated out here. Okay, and yeah, so this is A8 to A15 is separated out here. So from AD0 to AD15, using this particular logic, you can see this the clock input is triggered from the ALE, which we have already discussed of the processor. So we demultiplexed higher order address lines with this particular thing, and then we demultiplex lower order data lines from this particular thing through this 74245. 74245 is basically is 74245 is basically a data bus buffer, a transceiver. It is a transceiver. Okay, so it has been taken here, and 74138 has been taken here. This diagram is not actually using our idea. This only tells how 74138 can be used, where ABC is a alternate name for S0, S1 and S2. The selection lines, they are connected to here, and then the G2A bar, G2B bar and G signals are being connected here. So you need to have such a kind of arrangement here, and then this we will discuss in our next class. Now you concentrate only on this switches. So we use 74244, which is an octal. Octal means 8 number of tri-state buffer. Tri-state buffer. Let me turn off my video capture. Yeah. So octal tri-state buffer, octal tri-state buffer. So as you can see here, the inputs are connected, the same arrangement that what we have discussed. The input 0 is connected to a pull-up resistor to the VCC, the other end of the switch is connected to the ground, and a similar arrangement for all the 8 inputs, The outputs of the 74 buffer are connected to the data bus or connected to the data bus. Enable, the enable signal is connected from the output of decoder logic. In this particular case, they have taken it from yeah, the P0. So it's an OR gate. And then look at here, the OR gate, another input is coming from read bar. This is very important from the microprocessor. So what it tells is that this particular device will be enabled only when the processor is performing I/O read operation. When an I/O write operation is taking place, this will be 1. So this will also go 1 irrespective of the address. So these outputs will become tri-stated, logically disconnected. When a read operation is coming, this will become 0 and the device is selected. When the device is selected and this is going to become 0, the switch status will be momentarily put into the D0 to D7 bus and then taken inside the processor. This is the basic idea. This is the basic idea. So I'll stop up to this because time is up, and I will give you a couple of questions. I will be giving you a couple of questions for you to answer to assess whether you are able to understand this or not. Right. So after you watch this particular video, you please answer those questions also, which will be part of your attendance for this particular class is considered. Okay. Thank you all. So we will again meet in another class.